Okay, so we left off talking about vectors, right? And these are just these simple way of organizing a list of data. Um, and their use might seem a little, I don't know, pointless. Why would you have them if you've got data frames? And to some extent that's true, right? There's always some fancier way we can do things that can do the thing that a simpler thing can and more, but often we want to just keep things as simple as possible. That said, vectors are very useful for storing things and working through things. And one of the reasons for that is because they match very, very nicely with a thing called a for loop. A for loop is when you want to do the same thing to every element in a vector. It doesn't actually have to be a vector, some kind of organized list, but we're going to work with them in vectors quite a lot. And so for loops are, on one hand, very simple. On the other hand, they're kind of confusing a little bit. We're going to start with just ignoring the fact that they're designed to go with a list and just use them in the simplest possible way that you can. And that's like this. So you start by typing for. Helps if you select this, for. All right. It's even coming up here with some tooltips about what it's going to say. It's saying for some variable in some vector, do something. It's pretty confusing what it's saying there. Let's not get worked up about it. What do? We start a round bracket like we're doing a function, a parentheses, right? And then we declare a variable. So this is the variable that is going to exist inside this loop. We don't need to make it beforehand. The for loop is going to make it for us. And let's just call it v for variable. All right, and we're going to say for v in something, in some list. All right, so we're going to say in, let's just say 1 2 5. All right, remember how we did that? If we go 1 colon 5, knows what that means. It means 1 2 3 4 5. It instantly changes that to 1 2 3 4 5. And then we open these curly brackets. We've seen this is our third time of bracket we've seen. And this is just called curly braces usually, right? And they are often used to surround some little bit of code. And all we're going to do is we're going to go print v. Okay, so what what is going on here? Okay, so we're saying for every element in this thing here, this thing being in this instance the numbers 1 2 3 4 5, we're going to do something. And what's going to happen is this variable v is going to take on first the value 1. We're going to execute this code here. When that's done, when it gets to the curly bracket here, it's now going to take on the value 2. And it's going to run this code here, where now v is 2, then 3, then 4, then 5, right? So for every element in 1 to 5, v is going to take on the value of that element, and then we're going to execute this code. So this is not going to be super exciting, right? But when we press enter, we get 1, 2, 3, 4, 5, right? First v took on 1, then it took on 2, then it took on 3. Okay, so I think we've still got our myvec from before. All right, 1, 2, 3, 10, 22. So we can do the same thing. 4, 4, 4 v in myvec print v. 1, 2, 3, 10, 22. Right? So that's pretty good, right? So we didn't need to like, how can I put it? It knew that myvec was a vector. It knew that it was going to get the first element, the second element, the third element, the fourth element, the fifth element, right? And print them all out. Now we could have done that in a slightly different way, where we could have said something like this: for v in 1 to 5, print, go away all those tooltips, open brackets, and now we're going to say myvec square bracket v. All right, now that's quite a lot to take in, so let's just have a moment, have a chill, have a relax. What is going on here, okay? So for v in 1 to 5. So v is going to take on the value 1. We're going to execute this code. We're going to take on the value 2. It's going to execute this code. 3, 4, 5. And each time v is going to go 1 in here, so we're going to get the first value from myVec and print it out. Then the second value, the third value, right? Now this is plainly a bit more of a long-winded way than this. There could be reasons for doing one or the other, but let's just run this and make sure it works like I think it will. There we go. Okay, just the same kind of thing. Pretty good. All right, so for loops are when you want to go through some list and you want to do something to every element in that list. And it doesn't, as I said, it doesn't actually need to be a vector. You could go through all of the rows in a data frame. There's all sorts of ways you could do this, but it's pretty useful. And just so we make sure we're all sort of getting this right, you can also do it with other kinds of lists. So if we go names equals C, and we can do like Abid, and we can do, Bing, and we can do Chris, right? And now we have our vector of names, so we can go for name in names, print name, right? So name takes on the value of each of the elements, first Abid, then Bing, then Chris, and then executes that bit of code there, which is just print name, right? And obviously, these are kind of completely toy silly examples because we could have also just gone print names, right? And got these to print out, right? But the point is I just want to get you to grips with this for loop, this idea that we can iterate through a list and do something useful with it. And so I gave an example in the online content where we wanted to just do some interest rate stuff, right? So let's just go through it. So, the point of a lot of these, no, that's wrong. Often we work with simple systems that turn out to be kind of complex when we look at them in their totality, right? And often we cannot know how they're going to behave in future, right? So this is the kind of stuff that chaos theory was born from, right? Chaos theory started, they were just trying to look at some simple equations that they thought were pretty basic, pretty boring, right? And they ran them and they got some kind of weathery kind of stuff going on, or some heat rising and some rain falling down if memory serves. They thought that's all very well and good, and then they ran the simulation again the next day, and it didn't do the same thing as it did before. And they're like, "What's going on? This is just maths. How can simple maths come up with different values?" It turns out that simple equations can sometimes have crazy results. And this was only possible because of computers, right? So we're going to be moving in this direction of Lorenz, who was the person who ran these simulations and sort of chaos theory was born. We're going to move in the direction that we're not going to get to anything quite as complicated as what he did. But as I say, the point was he started with what he thought were a set of simple equations and got some quite complicated results, and we're going to do something similar in the fullness of time. But let's just start with something super simple, which is interest rates. All right. So let's say I start with $100. So let's go starting value, starting val equals $100. All right. Now, okay, so we've got a variable starting value, it's holding $100. Now, how does interests work if we're trying to save, right? Well, we get our newsflash, I am not a financier here, right? So I'm going to say some stupid stuff, but I appreciate the maths even if I don't know the words, right? So what we get is we get the money we have plus some interest rate, let's say at 0.5%, we don't need to put in the percent symbol, it's 5%, times what we have in the bank, right? And so that is what we would get, starting val, whoa, $105, right? 5% interest, no bank fees, you know, we'd all be so lucky, okay? So that's what we get in a year, all right? But the question is, what would we get in 10 years? All right, so we could go through and do this over and over and over again, or maybe we can get the computer to do it for us to simulate it. Now, it turns out there is a simple equation that we could put all this value into. We're not going to do that, right? Because we're lazy and we can't be bothered thinking that hard. So we're just going to get the computer to do it for us. So what do? We're going to say for t in 1 to 10. All right, so t is going to take on the value 1, 2, 3, 4, 5. We're not even going to use t. We're just going to go starting val is equal to the starting val plus 0.05 times starting val. All right, so this is the kind of stuff where mathematicians and computer scientists all of a sudden freak out. What am I saying? Why am I saying starting val is equal to starting val plus something else? So they're plainly not equal. No, what I'm saying is every year, this t represents how many years. On the first year, we're going to do this maths we did above, where we say how much money is in our bank account. Well, it is the money we had plus 5% of what we had. So at the end of the year, this is what it's going to contain. But then the next year, we're going to do the same thing. Well, next year it's going to be $105 plus 5% of $105, and that goes in, and we run that over and over and over again. We press enter, and then we say print starting val. And if I've done that all right, this is going to be $162. All right, the power of compound interest. So this is a for loop being used in a slightly more profitable fashion than just printing out lists, right? It's computed something that we didn't know before. We know now that in 10 years of 5% interest, if it's compounded annually, we should get $162.89. Pretty good. Okay, now we use this trick where we calculated the value of the next year from our current value. And anybody who's done any calculus should start to see that this starts to feel a bit like a differential equation, but this is the last time I'm going to mention differential equations, right? We are just going take our current value, do some maths to it, and get our next value, right? And this is what they did, what Lorentz did when he discovered chaos. It is what Hodgkin and Huxley did when they described the action potential. It's how Newton described gravity and acceleration. It's this idea that we can describe how things evolve over time by taking our current value and doing a little bit of maths to it, and it will generate our next value. And so we're going to go into some slightly more biomedical ideas in the next video.